Hello and welcome again. In this video, we will study an interesting and important concept from the group theory, which is called centralizer of an element, and also we will see an example. Okay, we start with the definition of centralizer of an element in a group G. Let A be a fixed element in group G, then the centralizer of this element A in G is denoted as C of A, which is centralizer of A, is the set, in fact, subset of G of all those elements of G that commute with A, which is fixed element. Which means C of A is actually those elements G of group G such that these GA commute with A, means GA is equal to AG. Okay. Again, we take the example of dihedral group in D4, which is group with 8 elements. We have the center of identity element is the whole group itself, D4, because every element is commute with center, and also every element compute with identity element. Also, the center of R180 is the whole group D4. But for the elements, for example, R90, the rotation with 90 degree, its center is identity itself, R90 itself with R180 and R270. And this is the same, means the center for R270 is again the same set, identity element, rotation with 90 degree, rotation with 180 degree, and then rotation with 270 degree. Okay, now we are going toward an interesting result, which is the theorem that the centralizer of an element is subgroup of group G. Okay, proof. Let A be any arbitrary element of G. Now we have to show that centralizer of A is subgroup of G. Okay. Clearly, the identity element commute with this element A. This means, by the definition of centralizer, this E belongs to centralizer of A, and this shows that the centralizer of A is non-empty set. Okay, we will use the two-step subgroup criteria. We consider two elements from the centralizer of this element A. Since x and y belongs to centralizer of A, this means that x commute with A and also y commutes with A. Okay, now consider x, y, A. Since the associative law holds, so this can be written as x into ya, and we know that this ya is actually equal to ay. So this can be written as x into ay. Again, using the associative law, this can be written as xa into y, and we know that this xa is equal to ax. So this is equal to ax into y, and again by associative law a into xy, and that was actually equal to xya. It is clear that this the product of two elements xy is also commuting with a. This means this xy belongs to centralizer of a. Now we have to see that we have to show that the inverse of elements, which is x inverse, also belongs to centralizer of a. Okay, consider the proof is exactly the similar as the proof of center of a group. Okay, we consider xa is equal to ax. We pre and post multiply with x inverse, and that is equal to x inverse a x x inverse. Using the associative law, it can be written as x inverse x a x inverse, and here x inverse a into x x inverse. This x inverse and x, which is product of x with its inverse, it will be identity. So we will get a x inverse is equal to x inverse a. It is clear that the x inverse is also commuting with a. This means this x inverse belongs to centralizer of a. Now by two-step subgroup criteria, it is proved that this centralizer of a is a subgroup of group G. It is clear that the centralizer of every element of G is making a subgroup of G. So that's all about this video. Thanks for watching, and please subscribe the channel and like the video.